Okay, hello everyone. Welcome to our Monday seminar, which is also the first of the year. Today it's a great pleasure to have with us Michael Trott, who will tell us about the SMEFT. Michael, please, you have the virtual floor.
Okay, so I hope everyone can hear me. I'm actually doing a thing where I have my slides on one Zoom and then my video is on my cell phone. So hopefully this will work. So thanks very much for the chance to give this talk virtually. And I'm actually in Madrid for the next week or so. So if anyone actually is interested in this and wants to have a further discussion on this, consistent with COVID restrictions and such, if you wanted to meet in a cafe or something, we could maybe chat about it a little bit if there are some questions. But also please ask questions during the presentation. So what I'm going to talk about is the geometric SMEFT. So this geometric approach to the standard model effective field theory, which is something that's been taking off in the last couple of years, as you can see on the bottom of this introductory slide. It's a bunch of papers for a lot of people connected into the group in Copenhagen. But there's also some, more junior people and some other groups starting to be involved in this as well. So what the key point is that I want to get across with this discussion is just the following. Let me just declare it right up front. So the key point is that even though the standard model effective field theory can be formulated and studied as people traditionally have been studying it for about the last 10 years, just as an effective field theory, bottom up, straightforward sort of thing, there is great benefit to appreciating the idea that this theory actually has a geometric structure. And it allows you to do calculations that you have great difficulty possibly trying to construct in the more kind of standard old approach to the standard model effective field theory. So if you appreciate that there's these geometric structures, which I'll talk to you about, then it allows you to do calculations that are very difficult, if not impossible to do, more bottom up. So that's basically the main point, and that's the reason why, because a couple of us are thinking about things geometrically, we're able to do this explosion of papers that you see at the bottom of this slide. It makes things very easy that otherwise are very difficult, if not impossible, in the usual approach. So this is work that you'll see is done with a bunch of different people. I want to highlight the people in black and white on this slide are postdocs. So they're looking for grants and they're looking for permanent positions, and they're doing a lot of really good work. And there's also one particular name, which is a master student at the bottom here, which Tyler did a paper with at Niels Bohr. So even master students now are jumping in and doing this sort of thing. It's tractable to do that sort of thing at that level. So let me go on and let me get moving here. So I'm going to tell you first a couple of things, remind you of a couple of things about the SMEFT. I know there's a lot of experts locally at IFT in the SMEFT, but I'm going to just remind you of a couple of things about the SMEFT with the eye towards what are the aspects of the SMEFT that the geometric approach actually addresses and helps in terms of our calculational ability. So a quick reminder of the SMEFT, it's basically a straightforward interpretation of what we have discovered at LHC and what we have not discovered at LHC. So it incorporates the existence of 125 GeV scalar, that's as far as we can tell, 0 plus, consistent with the Higgs. And that's very clear in these resonance bumps here from ATLAS and CMS. And what it also incorporates is the knowledge base, which has been gathered over time, which is that basically there's a lot of approaches for physics beyond the standard model, a lot of models for physics beyond the standard model. And if they have mass scales and resonance features and kinematic features that the data could show at the range of like TeV scale and below, many of these models have been searched for. This is just a plot listing a whole bunch of them. And they have not been found, these particular kinematic features or bumps that they're looking for, or particular particle contents showing up in various ways with decay chains. And because we know more about what's in the spectrum and we know more about what's not in the spectrum, we can do an effective field theory approach exploiting that information. So that's why the SMEFT has been taking off the last 10 years, of course. So down here, we have, of course, the electric weak scale states, including this 0 plus scalar that's in the spectrum and assumed in this structure in the SMEFT to be embedded in an SU2 scalar doublet. And up here, we have a red shaded region where our hopes for physics beyond the standard model are being largely pushed. It's not a completely model independent statement to say that you are being pushed up to higher mass scales for considering physics beyond the standard model, but it's quite a comprehensive statement, even though it's not completely all possible models being excluded for those mass scales. You could have light particles with small couplings, of course, but this approach in the SMEFT is basically focused on the possibility of physics beyond the standard model, which sits in the few TeV region. in this red shaded region, which is like physics beyond the standard model is reasonable to hope for, a loop factor above the Higgs mass. We don't have perfect experimental reach into that region, and the SMEFT techniques would possibly show these perturbations showing up in the data if we use this sort of approach. So that's kind of the sweet spot for the standard model effective field theory studies. We're thinking about physics in the few TeV region, and we're trying to do a more model independent approach, changing the approach from assume the model, do the exclusion bound, move on to the next model, to do a global sort of interpretation in terms of local operator Wilson coefficient constraints, and then try and find some deviations and then follow the data to see what it's telling us. This is just the standard approach. And the reason it works is that deviations look like local contact operator effects in effective field theory. You're doing a Taylor expansion, and there's a small expansion parameter, which is essentially this small shaded region mass scale divided by this larger mass scale. That's less than 1 because this is a log plot. There's actually some significant numerical separation going on now with this expansion parameter being less than 1. And doing this approach is quite straightforward and quite standard. And of course, a lot of experts are locally at Madrid on this, so I don't want to belabor this point too much. Now, this works, and it still works in the geometric SMEFT because essentially the decoupling theorem is telling us that the heavy mass scale, this red shaded region, possible physics beyond the standard model, is being now controlled in the way it appears in the data in terms of perturbations. So if we have a prediction for the standard model, we have the leading standard model effect for some expectation value. And then we have this heavy mass scale dependence sequestered in inverse powers square into the 4th power. We get local functions, and we have in the numerator possibilities of either the VEV itself or kinematic factors that have to do with the Mandelstam, in this case for 2-to-2 scattering, but it can be some other kinematic factors for other sort of scattering topologies. But the point is that this sort of is a controlled expansion. It's consistent with the data, and this is the core idea. So usually in the case of the standard model effective field theory, people set things up this way, and then talk about how when we do the standard approach of thinking about the standard model effective field theory, we get constraints, we get global fits, and where we are. And that's also very important work. But to push further beyond the kind of state of the art that's been established by many groups now, I think the geometric approach is very helpful, as you'll see. So the physics beyond the standard model is then organized into local operators that have these IR operators have long distance propagating states in the interactions. And then the UV dependencies in the Wilson coefficients divided by the cutoff scale. Here it was M heavy, but generally speaking, it'll either be suppressed and absorbed into the notation for the Wilson coefficient of what you see going forward, or it's going to be characterized by a lambda. Okay, so that's very straightforward. And the only issue is that it's hard to push this systematically forward, even though you can just turn the crank and keep going for years and years into the future. Now, why is it hard? Well, there's lots of difficulties. One of the difficulties that shows up in doing the SMEFT is just the number of parameters that are there, even at dimension 6, when you start to think about interference with the standard model. So this is just a count that we did many years ago in terms of the number of parameters there at dimension 6. And there's a couple of things I just want to emphasize here, going to the direction of how the geometric approach helps us go even beyond dimension 6. So one thing is, it's just a lot of parameters. So this 2,499 number is the addition of the CP even and CP odd number of parameters. The number of parameters is strongly associated with fermion indices and the operators that are 4 fermion operators. So if you just have one generation, you have 53 plus 23, and that's about 70-ish, and well, 76. And that's a lot less than 2,499. So a lot of the structure, a lot of the number of parameters is associated with fermion indices, and therefore it's going to be associated with flavor assumptions, flavor changing effects. So when people doing SMEFT studies at dimension 6, they basically are not doing fits to 2,499 parameters, they're doing fits to like 20, 30 parameters. But, and a lot of that has to do with the fact that they're focused on the appearance of the parameters in some observables which don't have a lot of flavor indices around. There's assumptions that are sometimes used in terms of the flavor structure of physics beyond the standard model represented in the Wilson coefficient and its flavor pattern. And there's also the effect that when you interfere with the standard model, the flavor changing effects of the standard model, it's a hierarchical symmetry breaking pattern in the standard model for flavor changing effects. So if you just interfere with the standard model, it projects out a lot of flavor changing effects associated with this multiplicity of flavor indices. So at the end of the day, when people are doing dimension 6 sort of fits, they're down to like 20, 30 parameters. Maybe it'll get up to like 30 or 40 in due time, but it's not 2,499. And there's no expectation it'll be 2,499 in the near future or in the far future. No one's really going for that. But it is a legitimate question to ask, well, what about all the other parameters that are there at dimension 8 from cross terms at dimension 6 or dimension 8 operators themselves that are feeding into these fits that are being done with 20, 30 parameters with people interfacing with these global fits in the data? how many more parameters are actually there, consistent with all the assumptions and all the sort of way that we're studying the data just at dimension 6 when we're trying to learn something. When we neglect those number of extra parameters at dimension 8 and such, how bad is that in terms of our ability to learn from the data? So that's what the geometric approach is going to help us with a little bit, and getting these parameter counts under control. So it's not just the total number of parameters. Another thing the geometric approach helps with is understanding what the parameters are doing and how to think about the way the parameters are modifying our usual interpretation of the Lagrangian parameters in the standard model themselves. So a good example is just shown here. So when you work out essentially the dimension 6 effects of the modification of how we go from the weak to the mass eigenstate basis, what you notice is there's a particular Wilson coefficient, this one CHWB, there's a suppressed lambda squared here, that it comes along multiplying the VEV, and it changes the rotation, it changes the meaning of the angles in a correlated way. And there's also a couple of other Wilson coefficients, but really this particular Wilson coefficient has this role which goes along and does a lot of correlated changes. Now that all comes in proportional to the VEV, and it's just a bit confusing, even at the dimension 6 level, how that works out. I mean, it's all been sorted out now in the literature, but the issue is how complicated is it going to dimension 8? And can we really do this tractably going even beyond dimension 8 in the future? And what you'll see is that we can actually understand this correlated change due to this particular Wilson coefficient and the way this structure appears here in terms of these perturbations changing our usual interpretation of Lagrangian parameters very cleanly and nicely in a geometric approach. It really cleans up our understanding in a nice way. So at this point in time, you'll note that there's Lagrangian parameters with bars on them. So those will just be at this stage in this discussion, canonically normalized Lagrangian parameters. But as you'll see going forward, these will be reinterpreted as geometric Lagrangian parameters, which are the equivalent of the standard model Lagrangian parameters, incorporating this geometric structure that's there in the field theory. The clue here is that all these complications at the level of just this one operator changing the weak to mass eigenstate rotation in this correlated way is all proportional to the VEV. Okay, so that's basically the clue that we need to follow and think about pretty carefully as to what are the changes going on proportional to the VEV when we're having this effective field theory approach. Okay, so it's not just the number of Lagrangian parameters, it's not just the fact that they do some weird things in terms of our expectations and modifying weak and mass eigenstate rotations and that sort of thing. It's also the fact that we have to assign numbers when we're doing consistent dimension 6 sort of fits to the Lagrangian parameters themselves in order to make predictions. So here's just an example with muon decay. So at the level of dimension 6, we basically take what is usually the way that we assign a number to the VEV, the 246, and we have to have a modification that's consistent. It's due to the higher dimensional operators. When we do that inference from some experimental measure, in this case muon decay, and assign that information to a VEV when we actually make a prediction for some other observable. So usually in the case of the standard model, what happens at least at leading order or tree level is that this Wilson coefficient for this low scale operator is assigned to the VEV from this measurement. In the case of the SMEFT, just at dimension 6, we have a modification of this vertex, we have this vertex that's also changed. Those two combined effects show up here, and it's just symbolized by this delta GF at dimension 6 here. So if we only used the measurement of the VEV in terms of muon decay for all predictions involving the VEV, if we always have this combination of Wilson coefficients for all predictions, it was always following around the VEV in a consistent way for everything we possibly predicted, it was always associated with muon decay, the VEV, then we would not really have an effect. It would just be absorbed into the numerical value of the VEV, and there wouldn't be any difference. The point is that we use many times predictions which really just depend on the VEV and not this way that we extract and assign the numerical value to the VEV. So we have to basically do a correction factor for that at dimension 6 and pop that correction factor out all over the place in all sorts of predictions. Now that's pretty well understood at this stage and it's being incorporated into the dimension 6 fits. The problem is, what about the going to subleading order? What about the dimension 6 squared stuff? What about the dimension 8 stuff? When we do this sort of inference, which we do for all the Lagrangian parameters, making all these predictions, is it really tractable to get all of that under control and assign those numerical values in a consistent way, neglecting all those subleading terms? And again, how much does that affect what we think we're learning from the data? So these are the challenges that are basically in our face now that we've got the dimension 6 technology developed to the point that it is. Okay, this is kind of the state of the art, just to give you an idea of what people are doing and doing pretty well nowadays. They're doing global fits. They have Wilson coefficients, and what they get are basically combinations of electric precision data, some Higgs data, and some top data. In this case, this is shown from this group of Ellis and collaborators. And the important points to illustrate here are there's very hierarchical constraints. This is a log plot. Some things are very constrained. Many things are not very constrained. But what's always constrained is some combination of the Wilson coefficients. This color coding is basically a composition of some eigenvector in a Fisher matrix. Once you basically have diagonalized and found the constrained directions, it'll always be a combination of Wilson coefficients. And so some combinations are quite constrained. Many of them are not very constrained, but it's always some combination of those coefficients that you're talking about. And again, we want to understand essentially how this global study going forward, as things get more precise, is affected by all the stuff we're neglecting at dimension 6 squared and dimension 8, loop effects and these sorts of things, so that we don't fool ourselves and think we're learning more from the data than we're actually learning, considering all those things that we're actually neglecting when we're studying the data. Okay, so that's the current state of the art, and that's the way the challenges kind of land on our laps, because we push things to this level. We have these sort of glorious global fits, doing things very carefully and quite well nowadays in terms of interpreting combined data sets. And the experimentalists are, of course, doing this too. Okay, so if we want to go forward, the argument here is that understanding this geometric approach and these geometric field spaces is key to doing that in a consistent and basically systematically improvable way, and it's going to make things very easy that were difficult or impossible. So what's the sort of things that happens? This is the preview of what's going to happen. So here's an example of a perturbation for Higgs to gamma gamma being described in this geometric approach. So what happens is basically you have this perturbation, you have some kinematics associated with this 3-point function, and then there's a bunch of numerical factors that will appear here. And the important point is all of this is going to be interpreted as geometric structure multiplying the kinematic transfer function. This is actually going to be a Velbein, which is associated with defining an asymptotic state, which is canonically normalized for the Higgs field. We'll define this in a moment. These are variations of metrics we'll define. And you'll notice these barred Lagrangian parameters are showing up again, which before were just canonically normalized dimension 6 Lagrangian parameters, but here they're going to be the geometric corresponding Lagrangian parameters for the selector charge and these sorts of things. So this whole structure multiplying the kinematics is going to be interpreted geometrically. And that's basically going to give you an all orders answers when you interpret it this way in the VEV expansion, the V squared over lambda squared expansion. And you'll also notice that this sort of answer, it doesn't have a lot of intrinsic operator dependence appearing. So when we have Wilson coefficients, they're appearing in these geometric structures. When we change operator basis, we can change the individual appearance of Wilson coefficients, but it's always going to be a geometric structure that's multiplying some kinematics. So you're stepping also in this approach closer to a more operator independent approach to interpreting the data, which is actually quite valuable in terms of understanding what's going on, because in the amplitude perturbations, it really is at the end of the day always going to be kinematics times geometry. And that's basically what you're going to see is going to appear going forward. So we're going more in the direction of what's actually appearing in the amplitudes there and what's basically more field redefinition independent. So any questions so far as to the difficulties in the usual approach? And I'm going to get into the geometric stuff. No questions? Okay, it's all very kind of review and standard. So let me now get into the geometric approach. So the key thing which led us to this approach and other people to this approach was to understand a little bit more clearly and carefully what we actually discovered around 2012. So in the case of the Higgs, just to remind you, a way to think about the Higgs is that you take this Lagrangian at the top of this page, and when the Higgs takes on a vacuum expectation value, you basically have these green blobs, which is going to represent visually vacuum expectation values in this top consistently. And these H fields, which include one component, which is the Higgs, is then going to be expanded around this vacuum expectation value. And when that happens, what's interesting is that you get combinations of Lagrangian parameters and you get the masses, as we know in the usual Higgs mechanism. But what's useful is that basically all of that stuff is coming proportional to the VEV, a reorganization of the Lagrangian parameters that are there in the weak eigenstates are then present in the mass eigenstates proportional to the VEV. Useful things appear in terms of combinations of Lagrangian parameters proportional to the VEV. And of course, we have this usual interpretation of the Higgs taking up this vacuum expectation value of the other particles going through space and hitting the Higgs medium and slowing down, which is visually represented here. But going forward, when you think about this sort of thing, it's important to kind of think a little bit more carefully about what's happening in the case of the standard model. Because while that's happening, what's happening essentially is Lagrangian terms like this are being expanded out, and you're having 4-point functions like this. And then these two vacuum expectation values appear, and you have a 4-point function that's descending down to a 2-point function. So higher endpoint functions are descending down to lower endpoint functions. And that's kind of key to why the Higgs mechanism is working the way it's working. At this point, you get masses for the W and Z, and a massless photon remains. There's a useful set of Lagrangian parameters, the mass for the W and Z, that show up proportional to the VEV. But the higher endpoints are descending to lower endpoints. It's kind of a key thing that's happening. In the case of 3-point functions with fermion masses, you also are having higher endpoints descending to low endpoints. And this vacuum expectation is again represented by a green block. Now, when you go forward into the EFT and thinking about in terms of the EFT, what's happening is that in the case of the standard model, you have these higher endpoints descending to lower endpoints, but there's a limited number of higher endpoint functions to start with because of renormalizability in the standard model. When we started off with the Lagrangian terms we looked at before, because we're limited to dimension 4 and below, there's just a certain fixed number of Higgses you can have at tree level starting off, and you don't get infinite towers like you have in the EFT. But you do get useful combinations of masses and mass eigenstate fields and useful combinations of couplings proportional to the VEV up here. In the case of the standard model EFT, the difference is that we have a tower of higher dimensional operators. And we can have Higgs to gamma gamma now. One can have a dimension 6 operator, and one of the Higgs can get a VEV with this green blob. But that can happen at dimension 6, and you get a 3-point function. It can also happen at dimension 8 or dimension 10 or dimension 12. And while that's happening, you can contract the indices of the Higgs with symmetry generators. All of this stuff, the infinite tower of things now happening in the EFT, collapses down onto a 3-point function. And when it collapses down onto the 3-point function, a number of things have to happen. Well, one is you're going to get something which is an amplitude perturbation. That amplitude perturbation, which is close to experiment, can't depend on how you've chosen your coordinates for your scalar field. So something coordinate independent has to happen with all of those scalar dressings of this 3-point function. And on top of that, you're going to get some useful combination of Lagrangian parameters that has to do with all of this collapsing down of higher endpoints to lower endpoints. Just like in the case of the standard model, that's again going to happen. The key point is it's going to happen through geometries. And why are geometries appearing, and why does it have to be geometric? So there's 2 reasons, essentially, that it has to be geometric, this understanding. One is, in the case, it's Higgs specific. So you should get results that are independent of how you choose your coordinates for your scalar fields. If you take the H field and you write down its coordinates one way and someone writes down the coordinates in a different way, your answer should not differ in terms of how it actually is affecting a physical observable. And on top of that, you also know that essentially the results, when you get to measurable observable quantities, should be field redefinition invariant. So you should be able to do field redefinitions, change your field coordinates, change the operators that are there, and you should still get something field redefinition invariant. Different operator bases have different terms, but you should be able to get to something which is field redefinition invariant at the end of the day. So there needs to be some quantities appearing, some structure in the physics appearing that is independent of the scalar field coordination and also field redefinition invariant. And that's the geometric structures that appear addressing this amplitude, which I showed you on the previous slide. Essentially, it has to be geometric because you're asking the question, how do I characterize essentially the effects of this physics that in a way that is independent of coordinates? And the things that are independent of coordinates in terms of properties of spaces are the geometric properties of those spaces. That's why it's basically a geometric thing. But in this case, on the interaction terms, the Lagrangian interaction terms is geometry based on those.
Sorry, can I ask you something?
Sure.
I am Maria Herrero.
Yes.
When you probably you will mention in the next slides, but when you mention geometric thing, are you referring to the geometry of the full doublet? I mean, of the 4 components of the doublet, and therefore the quantities should be reparameterization invariant? This is the usual language in effective field theories, at least in the nonlinear case. I'm not sure you are talking about this.
What I'm talking about is a series of geometries, and it's essentially the interaction terms of the field theory. When they have scalar dressings, are going to define a series of geometries. I'll define a set of them for you in a moment. And in this case, because it's the SMEFT, I am talking about the full SU2 cross U1 structure with the doublet being present and assumed.
We are talking about geometries of the full 4 component scalars inside the doublet. It's not just the Higgs field. That's
correct. That's correct. That's correct.
Yeah. All right. So
so the geometric work that other people were doing was very focused on trying to look at a geometric approach. The past work of Manahar and Alonso, they started off trying to look at distinguishing the case of the heft and the SMEFT in terms of geometry. That's not what we're really focused on here. We're focused on the geometry of the standard model effective field theory itself, and in fact, the intersection of multiple geometries of the standard model effective field theory, where we've already assumed it's the SMEFT, and we have an SU2 cross U1 structure already embedded. Symmetry is going to constrain what I'm going to write down, as you'll see in a second.
All right, I will repeat the question later on if I find a moment.
You'll see it in a moment. We're getting right there.
All right, thank you.
Okay, so again, this is what I showed you before. this is now just stepping closer to for you to understand this equation in terms of geometry. We're going to now define this geometric object highlighted in red and these ones highlighted in yellow. And I'll make the argument again as to why these are geometric dressings. Okay. Okay, so this is essentially answering your question for one of the geometries. So I can maybe explain it a little bit more carefully here. So the first geometry people realized was around, in the case of the EFT studies, was this one, the dressing of the kinetic term for the Higgs. Now, one should, of course, remember that this sort of approach has been showing up in field theory for many decades before the recent work that myself and other people have been doing. It actually goes back to like the late 70s and the early 80s. People understanding pions this way geometrically was something that was about. And the Russians had a program of understanding this sort of thing, including this paper by Volkanovsky. So there's a lot of different aspects of this showing up in field theory in a lot of different areas. What's happened more recently is it's been applied to EFTs and a little more systematically to EFTs. So let's just look at this particular one and try and answer your question a little bit more carefully. So first of all, you can just think of the idea like the Russians were doing. Can I take the kinetic term for the Higgs and can I dress it with an arbitrary function with indices ij? The indices ij here run over 1 to 4, which is the coordinates of the scalar field. And you can ask yourself the question, can I do field theory with such general objects? Usually this is normalized in some simple way in the case of normalizable field theories. But if I think of a scalar background, can I just do field theory with this sort of approach? And the answer to that question is yes. And that's what this particular Russian was focused on. Now you can do a lot of work and there's a lot of benefit thinking about this as a general structure without any operator representation, which has symmetry constraints associated with the SU2 crush U1 doublet nature of the scalar field. But it's also quite important and interesting and useful to think about the particular operator representation where you have gauged local symmetries around that is basically going to dictate that this is not a completely arbitrary object. So when you have the operators in the SU2 crush U1 and gauged operators around in a particular operator base, you'll have a particular representation and this of this metric. In this case, it's and because we're doing small perturbations around the standard model, the standard model case is the ones in the diagonal. And the small perturbations is basically because we have v squared over lambda squared, which is this tilde notation. This is always an h tag ratio for lambda squared times the Wilson coefficient. And in a particular operator base, the Warsaw basis, you get this particular perturbation. Now, the limiting assumption associated with what you were asking just a moment ago is that you don't have arbitrary entries here. You basically have zeros, which are dictated by symmetry, gauge symmetry. And it's not arbitrary, it's not a chaotic matrix, okay? It's perturbing the standard model for one thing, and it's also limited in terms of where the zeros are and where entries can be non-zero because we have a gauged local symmetry here. And that's where the assumption of this SMEFT comes in. Different operator bases can have different perturbations, but they will have all consistent SU2 crush U1 symmetry constraints. And they will have different metrics, but those metrics will always be constrained by the symmetry. And this, in fact, is the square root of the metric. It's essentially a Wilbine. And we're going to see this is a very useful object to think about. And when I say metric, what I mean here is metric based on an interaction terms in field space. Okay, so this is not metric in the sense of space-time. It's that there's these interactions, and this is a two-component object, which I'm calling a metric, which this is a field space that's being defined. And there's distance measures on this field space. That's what I mean by metric here. You can take this metric, and in the usual way, you can define properties of the space that's it's defining, including its curvature. You can calculate a Riemann curvature tensor, and it's not zero. And that's kind of how it gets topologically interesting. When you go back to the work of Alonso and Manahar, and people trying to distinguish the heft and the SMEFT, then you're basically trying to do different curvatures and what curvatures are allowed or not allowed in a coordinate independent way, trying to distinguish those two theories, which is a certain question that you can ask, but that's not really the question we're going to be focused on here. So hopefully that's clear. This is the first interaction space that's appeared, and it'll always appear in red, one associated with the kinetic term of the Higgs and its dressing. And then there's another one, which is first showed up in this gauge fixing work we did. And this is another dressing of the kinetic term, in this case for the Yang-Niels terms. This A and B runs from 1 to 4. It's the W, 1, 2, 3, and then B. This is a generalized Yang-Niels term. And just like in the case of the scalar field dressing the kinetic term for the Higgs, you could say, well, can I do field theory with this as a general object? Sometimes you can think of it that way as a general object. And it's also very useful to think of it as something which has the gauged local symmetries of that object being imposed in a particular operator basis representation. And then you could have that metric with a representation in a particular operator basis, and you can take the square root of that. And in this case, it's again, small perturbations around the standard model. There's ones in the diagonal, which is the flat field space limit of the standard model. And then you have these perturbations, which are again constrained by symmetry that appear in a particular operator basis. This is a distinct metric. It's a distinct interaction field space associated with the Yang-Mills terms. So what you should do is you should start to think about SMEFT physics as really the intersection of multiple geometric spaces descending from these sort of objects we're defining in this way. They're the objects which are defining the geometries of the Higgs manifold, essentially, that's there underlying all the interaction terms, because we're generalizing the renormalizability and the renormalizable field theory into a non-renormalizable field theory, which critically, because of the case of the Higgs, is actually extending it into a geometric curved space, because all of those interaction terms of the Higgs, all of those dressings of the Higgs is going to vacuum expectation values, generalize the standard model Lagrangian terms onto a medium, which is the Higgs medium. And that's actually a curved background that you're actually generalizing your Lagrangian terms onto. There's multiple geometries associated with that. That's conceptually what's going on. So now this one will be always highlighted in yellow, and so it'll be showing up in that way consistently. You can think of it in multiple ways, as I've just said. Okay, so here's the great benefit of thinking it in terms of a general object, not the particular operator representation, but the general object that you could write down. You could ask yourself, if you wrote those two terms down, and then do a transformation from the weak to the mass eigenstate basis, and you just demand to yourself that you have asymptotic states with a well-defined generator for the weak and the mass eigenstates producing these states. Can I consistently transform from the weak to the mass eigenstates in terms of this general object before I do the operator representation expansion of it? If you do that, you find self-consistency in the math dictates that you have to have the Lagrangian terms generalized in the way that's on this page. So these G2 bars, GZ bars, and E bars you saw before when they were just canonically normalized Lagrangian parameters at dimension 6. They're still that here, but they are also, when they're written in terms of this general term, this 1-1 entrance in this metric, in this particular metric, they're also the general geometric Lagrangian parameters associated with generalizing those Lagrangian parameters to the curved manifolds, the Higgs medium, essentially, that these interaction terms are defined of. This is, again, it's driven by consistency in the math of doing the generator transform to weak to mass eigenstates in a consistent fashion, saying I have a well-defined asymptotic state in the case of the mass eigenstates. So this consistency condition also does something interesting. You'll notice the appearance of this cosine here and sine here with a theta z, and also this sine theta and cos here. Those two angles are actually distinct. They are not distinct in the standard model. They're degenerate. They're not distinct even at dimension 6. They're still degenerate, but they're first distinct at dimension 8. And you start to realize that you have to introduce two of them to that generator transform consistently. And then when you actually expand out to dimension 8 in any operator basis, you start to see, these are actually distinct things that had to be a possible distinction that we could just see experimentally. But you first could really understand that with this geometric approach, that those two things need to be there just to have a well-defined asymptotic state in both cases. You notice that the red appears here for this particular metric, dressing and defining these barred masses. So the well-defined all orders, as you'll see in a moment, masses associated with the W and Z, and that transformation going from the weak to the mass eigenstates where the photon remains massless, it is associated with this metric that we've just seen on a couple slides ago in a very basic way. So this just comes about just doing consistency in math, going from weak to mass eigenstates. That's this paper, you can see the details of that. And it really does tell you that this sort of way of thinking is quite powerful if, in particular, you had an all orders understanding of these objects that we've defined as just general dressings of kinetic terms at this stage. And we actually do have an all orders understanding in the V squared over lambda squared expansion of these Lagrangian terms. And why we have that is actually another different piece of physics that feeds in here. So that's these guys. This is the all orders answer in the particular choice of the Wilson coefficient representation of the Warsaw basis, and it's like all orders expansion descendant for those two metrics that we've written down. Now, why can we even write these things down is basically a very simple piece of physics. Remember that these two things are essentially the scalar dressings of two kinetic terms, the case of the Higgs kinetic term and then the Yang-Mills Lagrangian term. But it's all of the kind of scalar emissions that can happen off of that at all orders in the operator expansion. Now, it just turns out because of completeness relations, like the ones given on the bottom of the slide here, there's not that many ways of having scalar field dressings of things where you have scalars contracted with other scalars or scalars contracted through symmetry generators with other scalars. If you start to write down all the possibilities just on a piece of paper and you just keep writing down more and more ways of doing those connections and contractions of indices, you'll find that very quickly you can start, because you have an SU2 fundamental, which is the SU2 cross C1 H field in this case, and its symmetry generator is always acting on that fundamental, the completeness relations come in and reduce a lot of the ways you could write down things which look different into structures which you already wrote down before at a lower mass dimension, just times h dagger h. Essentially, there's just not that many ways to contract up SU2 fundamental and symmetry generators in an independent fashion. And that saturates very quickly in complexity. And that's why you can write down these all orders answers in closed form. That's what's basically showing up here, that these are infinite towers with phi squared, which is h dagger h, times some things you wrote down at a lower mass dimension, dimension 6 up to dimension 8 for the most case. And these are just the two cases given here. Now there's this object here, which is a gamma. It's not a Christoffel, although we do have Christoffels in this sort of thing. It's just a way of writing down symmetry generators in the real scalar field representation space. You can look at the slides at the end. We can look at the backup slides if you want to see the specific definition of those. The key point is you can write down these things in closed form at all orders. And essentially, they're not that complicated. Once you go to dimension 8, pretty much you pick up all the structure, and then you just get h dagger h towers on top of it because of the completeness relations, because of the SU2 crush U1 symmetry that we're assuming here. So it's another way of answering your question as to what's being assumed and how it's affecting things. It's letting us write down these sorts of all orders answers. So we have these guys at all orders in the operator expansion. And we have the previous slide, which is these objects that if we had them at all orders in the operator expansion would give you these geometric Lagrangian parameters at all orders in that expansion. So basically we have the two pieces of the puzzle, they fit together, and we have an all orders answer for a bunch of very interesting things in the field theory. So what we can do with this is first we can clean up our understanding, and it basically came from a clean understanding of the transformation of the weak to the mass eigenstates in an effective field theory expansion of the form that we have here in this SMEFT, where we have all these scalar dressings and v squared over lambda squared terms that we can write down, dimension 8, dimension 10, all sort of thing. So in the case of the standard model, we want to have basically a transformation from the weak to the mass eigenstates. That's pretty straightforward. You just basically take the interaction terms to do that transformation. Now these guys are just simple Kronecker deltas. Those are the ones in the diagonal of the metrics, which we never really wrote down. We just contracted the indices of the kinetic terms in closed form. But those ones in the diagonal were basically flat field space limitations that were present to in the case of the standard model was normalizable. And that made just this transformation simple. It was just a rotation. There were just some rotation angles that we all teach graduate students, and they were basically defining the weak to the mass eigenstate transformations. You can also do this with the couplings and with the scalar field. It's very straightforward. Now, in the case of the consistent transformation in the SMEFT at all orders in the expansion, you basically write down the only thing you can contracting the indices in a consistent fashion, where you also have kind of the understanding that the square roots of the metrics are defining the asymptotic, well-defined canonically normalized states in the field theory associated with generators, like this generator given here. And then you have a transformation that is actually true at all orders in the v squared over lambda squared expansion. And we have these objects defined at all orders as well for the reasons I've already stated to you. So now it's not just a simple rotation. These guys were things that their transpose is equal to inverse. Now the transformation is the combination of those, contracting the indices correctly with the Villebein. And this is not actually just a rotation, it's a transformation. It's this combined operation, the transpose is not equal to its inverse, but it's a well-defined transformation in the field theory that we know. And we also know these guys at all orders. We can just expand it out, dimension 10, dimension 20, whatever we want to do with it.
Excuse me,
it's actually the only...
ask you something else. Sorry, continue the slide, and then I will ask you.
So all I was going to say in finishing this slide is that essentially you don't write down anything else that generalizes to all orders in a consistent fashion with the generators being transformed consistently. But do you have a question?
Yeah, sorry for the interruption, but I'm very curious about the subject.
No, that's fine.
Okay, going to the scalar part, I mean, in this same slide, what do you mean by mass eigenstate when you talk about the 4 components of the doublets? Because 3 of them are Goldstone bosons, basically.
Sure.
So that part I do not really understand. What do you call mass eigenstate in that case? In other words, I am worried about the gauge invariance of this business, because I'm not sure you can deal the same way the 3 components of the doublet, which are really the Goldstone bosons, the phi plus, phi minus, and K, with respect to the Higgs. In other words, do they?
Well, if you let me answer, can I answer?
Yes, sure, go ahead.
So we are not in trouble with gauge invariance because we actually did this transformation, understood this transformation as we were basically doing a paper, which is the one listed on this page, which is basically defining the Ward identities of the theory that come about due to the gauge invariance of the theory. So basically what we were doing is we were basically trying to establish the symmetry transformation relationships between endpoint functions that is following from the gauge invariance. And that is basically been checked at tree level. And I'll get back to it in a moment at the end of the talk. But it's also been checked at one loop that gauge invariance is not being messed up. In the background field method that we used, we had defined awarded entities, and we've checked them at both tree level and one loop as being consistent. So you can certainly do this transformation. And I mean, I think I understand what you're worried about. And you would worry about the gauge invariance of this. You'd worry about how gauge fixing works here, and if it all fits together in a consistent scale independent way.
Right.
These are good things to worry about, but that's what actually we've been checking, and it does work.
It was shocking the word that you use, mass eigenstate, when you put to the right, the arrow. Mass eigenstate is not a clear definition for the phi case.
I think you can choose a well-defined mass eigenstate associated with generators. That's what I mean by it. You do have to make a generator choice. You do have to associate some particular combination of fields with that generator, which you're defining to be your mass eigenstates. And I'm saying that such a choice does exist, and it does exist at all orders in the v² over lambda squared expansion. And it leads to constraints when you gauge fix between endpoint functions, and those are the awarded entities of the theory, which are the test of the gauge invariance and the usual way that we test that we're not screwing up gauge invariance. And that has been checked not only at tree level, but at one loop. It does work.
Okay, thank you.
Sure. Okay, so going forward, this actually gives us an understanding, which is a useful understanding in terms of what we were seeing before just at dimension 6. So dimension 6, I highlighted before to you that there's this appearance of this Wilson coefficient, and it's kind of appearing all over the place, causing modification of the angles, the rotation, and it's appearing in these canonically normalized Lagrangian parameters. And now we can actually understand what's going on there, because what was going on there, essentially, the general Lagrangian parameters I showed you a couple slides ago were being expanded out just to dimension 6. So essentially, we wrote down the result before, which was all orders in the expansion, and that was the generalization to the Lagrangian parameters, which were the curved space Lagrangian parameters. And then what was appearing here in this correlated shift appearing in the Wilson coefficient appearing in these redefinitions of things and how it appeared in this kind of complex way was a linear expansion of those geometric Lagrangian parameters out to dimension 6 order. And that you can understand being very similar to when you have some coordinate system and you want to describe a curve in a coordinate system, you could choose Cartesian coordinates or you could choose polar coordinates. And if you choose Cartesian coordinates and then you project that curve onto those Cartesian coordinates, you'll have a correlated transformation with sines and cosines of how you project it in terms of the structure, or you can write it in polar coordinates in a kind of a simpler way. So that's kind of essentially what we're doing here is we're figuring out the Lagrangian parameters, which are the ones that correspond to the simple representation in the curved field spaces that are around. And then this stuff that was appearing in dimension 6 in a complicated way was a linearized, expansion onto a coordinate system dictated by the operator basis that we chose that was very intrinsically linear. And that's the usual approach in the case of the SMEFT that we usually do bottom up. So this is just a way of understanding why we got this correlated transformation appearing in the dimension 6 terms. And it also gives us the ability to just take the results I've shown you before, go to dimension 8, dimension 10, dimension 12, and just expand out. And then you get all those answers. The corresponding transformations of this form are now known in closed form at all orders in the VEV expansion. You can just expand them, the results I showed you before. Okay, so this hopefully gives you the idea of the way we're thinking here, which is actually leading to some benefits in terms of calculation ability. So the usual approach to the SMEFT, as I just emphasized, this expansion, dimension 5, dimension 6, dimension 7, you just write it down and just calculate directly. But there's essentially an assumption, or basically a hidden assumption is slipped in here, which is that this approach actually also corresponds to like a linearization out of these field spaces at each order in the operator expansion. And if you actually start to think in terms of the geometry, these interaction field spaces which are being defined, then you start to think, well, shouldn't we organize our thinking in terms of the physics a little bit more closely related to these structures that are in the field theory? The way you do that, as you've seen in a couple of cases, is you take that SMEFT Lagrangian, and it's still the same theory, but you reorganize your thinking so that you pull apart essentially some terms that have to do with the scalar fields, the scalar field dressings of certain kinematic structures, and those can carry these indices I, and there can be symmetry generators inserted in there. And then the VEV expansion, when it appears, collapses these high endpoints to low endpoint. And then you have to dress other structures which have to do with essentially the Lorentz indices, the kinematic transfer functions that are around. And so we're going to split the theory up in this way, which when we expand out order by order will correspond to this, but it's a useful way to split the theory up because it's more related to this geometry dressing of kinematic terms. It's closer to what's actually appearing in the amplitudes. Now, when you do this sort of reorganization, you have to decide how to think about the derivative acting on a scalar field. And that is a mixed term in the expansion because it has to do with the VEV and it also has to do with the Lorentz indices. And we group it with this derivative expansion here for reasons that you'll see in a moment. This is the reorganization that we're doing in the Geometric SMEFT. Okay, so when you do that sort of thinking, I've introduced two of these objects to you. There's a couple more you need to do for 2- and 3-point functions and the things you can build out of 2- and 3-point functions and resonant regions of phase space. But there's not that much more structure you need to do this sort of thinking systematically for low endpoint functions in the theory, which is actually a really wonderful thing to do with basically simplifying kinematics when you have 2- and 3-point functions. So the objects you need in addition to the two I've shown you are the VEV, basically the potential itself, which is just a function of the scalar field dressings of derivatives acting on scalar fields with contractions of field strength tensors, field strength tensors contractions themselves with scalar field dressings, and then essentially the generalization of the Yukawa interaction, a possible anomalous coupling to fermion pairs of a scalar field, and dipole operator connections of that form, and then the similar results for the case of the gluon fields. This set of terms, if we could define it at all orders in the field theory, would be very powerful because it would let us do 2- and 3-point functions at any order in the v-squared over lambda squared expansion. And we actually do have all of these answers defined at all orders in the field theory. That actually is the thing that came out a couple of years ago. So there's a choice here in terms of organizing the physics for it to get to the point where you only need that small set of terms, which is associated with what we need to do physics of 2- and 3-point functions for CP even field space interaction. So what's happened here is we've removed derivative operators. We've basically taken the Warsaw basis, where it's approach to defining a dimension 6 operator basis, and also what appears in the Hilbert series. And essentially it uses the equations of motion whenever possible to remove out derivative terms if you can, to basically just organize the physics in a specific way. That's happening here too. We're removing out derivative terms if we can. We're using the equation of motion if we can to just organize the physics to get down to that minimal set of terms. That's a choice, and that's true that that's a choice, but that's basically the choice that you make in field theory systematically when you're doing effective field theories, because you want to make cancellations that happen otherwise at the level of S matrix elements happen earlier in the case of the theory in terms of your formulation at the operator basis level. So there's a choice being made here, but that's the reason for it. When you make that choice, you get these results here, and you get to start to see the structure I've been telling you is there in more than just the two particular objects we talked about. So one thing I emphasized to you is that when you have these scalar dressings of kinematic terms, kinematic transfer functions, essentially that there wasn't that many ways to contract the scalar indices with generators and with each other. And that's what's showing up here in terms of the independent sort of operator structures that appear in these objects as you go as a function of mass dimension. So at dimension 6, in the case of this Yang-Mills term, for example, if you go back a couple slides, you will see that there's 3 terms at dimension 6. At dimension 8, there's one more term that you can write down. You can write down before in terms of the possible contractions. But then at dimension 10, all you got is h dagger h or phi squared times we already wrote down at dimension 6 and dimension 8. And the reason for that is the completeness relations, and just symmetry is limiting that growth in the number of independent terms you can write down. Dimension 12, there's only 4 of these structures as well. So you essentially have the ones you had before times h squareds, or h dagger h or phi squared. That happens with all of these terms that I've been defining for you for the 2- and 3-point functions. And these terms actually have a very clean interpretation in terms of how they cause effects in experimental measurements. This was, as you saw, associated with masses. This was couplings and mixing angles defined in the transformation for the weak to the mass eigenstate basis. The other ones define triple gauge coupling, Higgs to ZZ, and that sort of thing, Yukawas, dipoles, and anomalous couplings to W of W's and Z's to fermions fields with possible Higgs emissions. So all of these things we have at all orders, understanding of them, and it's actually allows us to do all the phenomenology associated with this and build up complex sort of Feynman diagrams and resonant regions of phase space when these are the components building up that more complex region of phase space in terms of what's experimentally measured. So that's why this is actually a very powerful approach, and lets us do things at dimension 8, dimension 10, and dimension 12 if we want to. It actually tells us something in terms of the parameter counts, like I was saying before. How do the parameter explosions that go on at dimension 8 or cross terms at dimension 6 and so on and so forth, how do they project into the experimental measurements? Now, in general, the parameter counts are defined as a function of the mass dimension of the operator basis. So at dimension 6, that's defined by the Hilbert series. And in the Warsaw basis, that count you saw 2,499 was a smaller number than 3,045 at dimension 6. What's happened here is people have added the baryon number violating operators to the baryon number preserving operators, which is associated with the 2,499. But this is essentially that number. And you saw before that when you had one fermion index, it was like 76. And here it's 84 for the same reason. You're adding together a couple of extra terms. And then you go to dimension 8, it explodes up to this number. Dimension 10, it explodes up to this number. This is a log plot, and this is basically a line. So this is exponential growth in the number of parameters. On the other hand, I showed you with this saturation due to essentially the completeness relations and scalar field dressings of important phenomenology, such as 2- and 3-point functions in resonant regions of phase space, that you have these complexities saturated at some point. Always was characteristic in that plot I showed you, that chart I showed you. And that's these lines just shown on here with the same color coding as on the previous slide. So within this general structure of the theory, the general Hilbert series explosion, there's a subset of Lagrangian parameters that project onto some specific kinematic structures that actually don't explode in an exponential fashion. They actually saturate to a constant level, and that's associated with the v² over λ² expansion. So this is why when you do tails of distributions and you go higher and higher in the operator expansion, you will find that the number of parameters that feed in grows exponentially. Whereas if you focus on measurements near resonant regions of phase space, things to do with like pole observables in case of the Higgs or the Z decays, then you'll find the number of parameters that feed in doesn't explode exponentially. It actually explodes much more calmly. It's just going to be a linear growth in the number of higher order terms. And it's essentially something we already understand in terms of at least the tree level behavior at dimension 6 and dimension 8. So this is actually a very important difference in the way the number of general parameters grow versus the way they appear in different measurement classes. So my opinion is we should go this way in terms of interpreting the data as much as possible. And once we understand that really well to dimension 8 as an error associated with dimension 6 studies, and so on and so forth, then we should start to think about going in this other direction and take that solid knowledge and expand it out in the direction of doing tails of distributions where we're going to have a lot of parameter growth. That's much worse than the case of measurements where it's really dictated by the Vev expansion, v² over λ². Okay, so let's just see what we can do a little bit with this in terms of the case of Z decay. So what does this let you do? So here's an example. If we want to describe a W and Z decay to fermions at all orders in the v² over λ² expansion with possible scalar field emissions, what do we need in terms of this field theory technology that's now been written down? We need an understanding of the kinetic terms of the fermion fields generalized into these geometric spaces with all those G2 bars and GZ bars. We have that. And we also need to add to that a possible field space connection associated with scalar fields coupling to pairs of fermion fields and possible generators. We have that as well. This is also defined at all orders in the field theory in the Geometric SMEFT papers. So these two things added up basically describe this interaction vertex, arbitrary possible scalar dressings, and then taking those Higgs's to vacuum expectation values. So this allows us to essentially calculate any phenomenon associated with this, like Z decay at dimension 6, and then go instantaneously at dimension 8, just expanding to next order in a Taylor expansion. It basically gives you an answer like this. This is the coupling of the vector fields to the fermion pairs, and then this is a field space connection expectation value added to that. And this has to do with the generators again for the well-defined canonically normalized external states. And this is an all orders V over lambda answer. If you expand it a little more, you start to see the Z, the photon, and the W couplings. The leading terms are like you're used to in the standard model. The dimension 6 effects that people do in all sorts of studies are a combination of these things and then expanding these out to the usual Lagrangian parameters, which don't have the bars. But we now have these objects and we can just expand to dimension 8 if we so wish. So that's been done. And you have to know basically the decay widths, which again, these effective couplings feed into. It's quite straightforward. And then when you do that, you essentially have this understanding of this vertex. So then you have the standard model term, the term everyone essentially knows for a long time associated with dimension 6, which is a v² over λ² correction. And this, just to get you to understand what I'm showing you here, the way it's represented here is this is a particular coupling to fermion pairs with a particular chirality for the Z. It's the effective vertex here. And then you should think of this as being this number in this particular input parameter scheme times this shift in the muon decay definition of the Vev, plus this number times this Wilson coefficient, plus this number times this Wilson coefficient, and so on and so forth. And notice these are tilted, so the v² over λ² expansion is built into this expression. And it's just the same for all the other chiral couplings of the Z to fermion pairs. And this defines the dimension 6 result. And there's two numbers because there's the two input parameter schemes. And at dimension 8, it's similar. It's just this. And this is the sort of thing that no one could calculate before, but that once you have this sort of technology on your hand, it's very, very simple to calculate. We were able to calculate this just a couple of weeks once we knew we could actually do it and had our brains organized and thinking that we should do this. And you'll see there's a lot of cross terms associated with dimension 6 squared or dimension 6 times dimension 6. Hardly any of these are picked up if you just took some observable and predicted out to dimension 6, took that and squared it. The usual thing called quadratics is a very small subset of the structure. And so that it tells you something right away is a bit of a problem in terms of people just doing that. And then these are just a couple of extra terms at dimension 8 that appear, again, consistent with the fact that it's not that complicated going from dimension 6 to dimension 8 with this understanding. There's just not that many terms that are distinct to write down in terms of new Wilson coefficients appearing. And these numbers have the same meaning in terms of what I showed you on the dimension 6. That's how to interpret them. Okay, so we can just do this, and then we can basically look at Z decay, perturbations to Z decay in LEP, electric precision data, and see how it affects our interpretation. We thought we were learning things about dimension 6 constraints. How wrong were we when we had those dimension 8 effects around that we can now calculate? Well, in the case of this almost Z coupling to leptons, it's not that bad. These two lines here are just one particular dimension 6 perturbation, and that particular dimension 6 perturbation defined with Wilson coefficient values in this text squared. And then the shaded region is when you basically take the new terms that we could calculate and you basically vary around the effect of the deviation, not just being the linear term or the squared term, but actually taking those other terms around and varying them around with some sampling chosen for those other Wilson coefficients and distributions. And it doesn't really affect that much what you think in terms of what a particular deviation in Z decay would map on into in terms of Wilson coefficients. This is pretty under control. And this is kind of characteristic. Essentially, processes that are tree level in the standard model are under better control than processes that are loop level in the standard model in terms of the effect of the subleading terms and the operator expansion that we can now calculate. It's just kind of a general lesson. But it's not perfect. Here's an example of how electric precision data is being affected by these dimension 8 terms that you can now calculate. Now, there was a lot of heat generated by some doubts raised a couple of years ago by myself and some collaborators that the usual interpretation of dimension 6 constraints just coming from electric precision data naively interpreted, where you just all the dimension 8 stuff and dimension 6 squared stuff, you just ignore it, assume it doesn't do anything in terms of your interpretation, and how much would the dimension 8 stuff, once we could calculate it, actually affect that interpretation? Are we basically over-interpreting the data naively at dimension 6 alone? And so what these plots show you is how you can shift your conclusions at dimension 6 when you have the dimension 8 results you can now calculate around now and just see what happens in terms of your interpretation of the data. So at low cutoff scales, when lambda is about 1 TeV, this is what's usually called the S parameter and the T parameter. And these two regions are basically when you have just the dimension 6, the interpretation that people have done squared out. And then when you have the variation that has the other dimension 8 terms around and see how things change. All this is basically showing you is that your interpretation can be shifted for low cutoff scales. And when you go to higher cutoff scales, higher mass scales of suppression for physics beyond the standard model, things tend to converge. The dimension 8 effects get smaller, so that makes sense. But also you can see that there's some issues here in terms of interpreting the data. Things like the forward-backward asymmetry of the lepton, where we get a lot of constraining power because the vectorial coupling of the Z to the leptons is essentially numerically suppressed in the standard model. Well, the cost of that, thinking you get constraining power at dimension 6 from that numerical suppression in the standard model means it's very sensitive and very input parameter scheme sensitive due to effects at dimension 8 and dimension 6 cross terms. So this distribution is just showing you essentially how the shift is being affected compared to the standard model when you sample around those other terms and just see how those other terms can change your projection onto this experimental constraint. And it's quite a significant effect in terms of schema dependence, especially at low cutoff scales. So essentially, we need to be more careful in terms of how we're interpreting electric precision data due to all these neglected effects that we can now calculate. And this really has very important implications for future collider studies, where a very naive interpretation of electric precision data is being combined in with Higgs data. So I'm almost done. Let me just finish up. You can also do this for the Higgs to gamma gamma, you now understand this equation. This is the first time we actually calculated out and squared out a dimension 6 result and saw what happened, and then also looked at what actually happened at the full dimension 8 result. So if you just take the naive square, you just have the standard model case of the amplitude, you have the dimension 6 perturbation you can calculate before, and you just square that. And that's just this defined in this way for Higgs to gamma gamma. The actual result has some other terms, not surprisingly associated with dimension 8 and cross terms at dimension 6. If you look at what happens when you actually have those other terms around and then basically interpret the data, not neglecting them, but just having some variation that you assign in terms of how they can affect your interpretation, like what you saw with Z decay, well, suddenly you see there's a big problem. It's a problem that's characteristic of loop suppressed processes in the standard model, Higgs to gamma gamma and glue Higgs production. So what's going on here is a number of different things. Again, the lines are the dimension 6 deviations and the dimension 6 squared deviations for some particular chosen values of Wilson coefficients. And the shaded region is sampling around the other effects we can now calculate to see how they would affect our interpretation in terms of a deviation being mapped to some Wilson coefficient values that we thought we could just interpret naively at dimension 6. It's quite a big effect, especially for low cutoff scales. What's really happening here is essentially that the loop suppression of the standard model is also associated with the Wilson coefficients at dimension 6 can have a suppression pattern when you have renormalizable physics beyond the standard model project onto those dimension 6 Wilson coefficients, and that suppression pattern does not appear for the dimension 8 Wilson coefficients. So even though you go from dimension 6 to dimension 8 in terms of this shaded region affecting your variations around affecting your interpretation of the data, at the same time, you get something bigger by 16 pi squared going from dimension 6 to dimension 8. So those combined effects means it's much more sensitive to perturbations of the subleading terms. And that's just the reality of how these deviation effects basically project onto the Wilson coefficients when you have a loop suppressed process in the standard model. It's for Higgs to gamma gamma and also for glue Higgs. This is just the case. So that's a bit of a problem. And that's a serious problem for the experimental program, which I want to get back to in a second. I just wanted to show you this slide very quickly to just show you that you can do other things regarding the Higgs, other than the loop processes, the 3-point function. You can build up other endpoint functions. You can build up, for example, Higgs for lepton decay. This is just a piece of it. Higgs to ZZ, this anomalous vertex. It's again kinematics times geometric structure. This is the standard model like kinematics terms, and this is the case for Higgs to WW. And then there's geometric dressings. We have an interpretation of these that you've heard in this talk. And then there's other kinematic structures with other geometric dressings. This is at dimension 6, this is at dimension 8. And this sort of understanding lets you understand a little bit more efficiently what we need to put in code for the experimentalists to go from dimension 6 to dimension 8 in terms of interpreting the data, because these anomalous kinematic factors, that this anomalous kinematics here only appears first at dimension 8 for this off-shell vertex. And that is essentially telling you a little bit of information about when they do acceptance corrections and they start to study the data and think about when they do things at dimension 6, how much things will dramatically change due to their cuts going from dimension 6 to dimension 8. It's going to be associated with these sorts of kinematic differences, these sort of different anomalous kinematic populations are the things to worry about in terms of acceptance corrections going in your experimental study from dimension 6 to dimension 8. So this way of thinking actually organizes a little bit more carefully for the experimentalists how to think about to get to these dimension 8 effects and which ones they should worry about the most when they're defining their cuts. And getting back to something that was asked before, this structure that we saw in the theory, if it's really there, it should be something that survives gauge fixing. It should be something that you can check ward identities for. And it should be also something that basically makes perturbative calculations easier to do. And that is actually the case. All of those things happen, and all of those things actually come about. And that was where we started, essentially, is we started with a gauge fixing approach, which we wanted to do gauge fixing in the background field method. And the gauge fixing in the background field method had to do with this metric and had to do with this other scalar metric. These hats are the vacuum expectation values. And essentially, that paper was essentially trying to figure out how to gauge fix in the background field method in a way that doesn't disturb the geometries of the background fields that are there. And that essentially led us to understanding that these are the objects to think about. And then we start to do perturbative calculations with this gauge fixing term. Essentially, a lot of the calculation structure is a little easier to understand because you have ward identities around that tell you how to think about combining the different terms in the theory. One thing that's really nice that happens related to the question that was asked earlier is that if you have a background field method approach, then you know that you can do your variation with respect to the background field gauge fixing parameter, this term here, and you will get 0 in your effective action because it's independent by definition of the transformation of the background fields. From this, you derive very quickly these ward identities in the theory, which are the background field ward identities, which are very important set of constraints for the non-perturbative and perturbative expansion of the theory. So this constrains both the perturbative and non-perturbative expansion of the theory. And when you actually look at what it does in terms of implications for 2-point functions, it basically tells you that the photon behaves as you expect. In the case of the Z, this was the thing that really let us understand that this was a geometric theory. It gives you this particular combination of Lagrangian parameters in this 2-point function related to this 2-point function. In the case of the standard model, that's just the usual Z mass. In the case of the SMEFT, in terms of operator dressings, it is actually a very non-trivial effect that actually is combined up to give you the geometric mass of the Z appearing in this constraint between the 2-point functions of the theory. This is what I was saying before when I was saying we check this at one loop as well as at tree level. This non-trivial effect in the field theory, which is coming about due to gauge invariance, has been checked at both the at one loop level. This is actually the check of it for some of the terms. Tyler did a lot of really good work developing a code letting this happen automatically, and then it was checked by direct calculation. And very non-trivial things happen in the physics in terms of combining of 2-point functions to get to this sort of, consistency check of the theory associated with gauge invariance actually being established. And it does work. I'm pretty much over time, I think. So I think I'm just going to skip over this and tell you a little bit about this fix. So I showed you before in terms of Higgs to gamma gamma and glue Higgs, there's an issue. The loop processes in the standard model for the Higgs. There's a lot of sensitivity to the higher order operator effects like dimension 8 and dimension 6 squared terms. And essentially the issue is for the experimentalists, how do they deal with that? Because if they basically neglect a whole bunch of terms, and if by neglecting a whole bunch of those terms, they have huge errors introduced, which are bigger than their current experimental errors, then it very significantly disables the sort of SMEFT program in terms of interpreting the data for dimension 6 perturbations. So the first step of trying to figure out what to do is to basically calculate the result. And this is the glue-Higgs result. And it is out to dimension 8 and also one loop at dimension 6 consistently. Now, something that's important here in terms of trying to figure out how to fix this problem for them is that you have to realize that the operator expansion and the loop expansion are not independent. But what I mean is that they're essentially correlated expansion parameters. And you should understand that that's actually the case from what I just showed you, because that's what's showing up here. This is something that is constraining the perturbative and non-perturbative expansions of the theory simultaneously. So the consistent result out to dimension 8 and at dimension 6 at one loop is now calculated for glue-Higgs. And then what is the problem for the experimentalists? Well, the problem is they neglect a whole bunch of these terms when they interpret at dimension 6. And how do they think about this? How can they think about this? Well, if they just do a naive interpretation of the errors associated with neglecting those higher order terms, they'll have a huge error. So what we're advocating to them is that what they should do is they should actually do something inconsistent, which is a lot of a problem for me because I'm not all about consistency in the field theory. But what they should do, in our opinion, is they should actually fit to not just the dimension 6, but a subset of the higher order terms, project the experimental results and constraints onto those. And then the other terms that are going to be around can be varied around, and then the error will be subleading to their current experimental errors. Now, when you have the full result, the full answer is calculated to dimension 6, then dimension 8, dimension 6 squared, and also at one loop, you can check to see the consequence of doing something inconsistent like that in the power counting of the field theory. What is the thing to worry about? The thing to worry about is that you're not going to get an answer that's not basis independent, and that's just kind of nonsense in terms of interpreting the data. And when you have the actual result, the actual answer like this, you can check to see field redefinitions. You can perform the field redefinitions by hand, and you can just basically see how bad it is in terms of if they do this inconsistency in the power counting, introducing an inconsistency in terms of numerical size of the field redefinition sensitivity or the basis sensitivity that you would introduce. And that's also very small numerically. So even though it's inconsistent in the power counting of the field theory, I think that's the thing that they should be doing in terms of interpreting the experimental data, doing an inconsistency where they're absorbing some of these higher order terms into what they're projecting the experimental constraints, because otherwise the experimental program is quite disabled in terms of what they're going to be able to do going forward, because the two processes that they have their most constraining power are going to have a lot of errors associated with them just because of the neglected higher order terms in the theory expansion. So that's it. Sorry, I'm a little bit over time, I think. But that's the basic point of this talk is this message, this sentence. The Higgs physics, if you understand it this way, if you understand that there's these curved field spaces around, they let you do calculations you can't do before. And they let you basically understand the symmetry structure of the theory. They let you basically do calculations and combining dimension 8 effects with loop effects consistently on this background Higgs medium. And this is quite important for the experimental program because Higgs physics really is the physics of curved field space. and it lets us basically move forward with some constraining and global fit programs in the future with these higher order terms now understood. So I'll just stop there.
Okay, thank you, Michael, for this very nice talk. So as we are running a bit late, we have time for one or two very urgent questions from the audience.
I have one, but since I have done many, I postpone to others. I have one question, if I have time.
Sure.
Maybe Jacopo, who raised your hand.
Yeah.
So hi, yes, I have a question. More than, I mean, I don't know if it's urgent, but since I'm not there physically, either I ask now or never. So you mentioned this Russian, this Vilkovinsky, when you introduced the geometric approach, basically. So my understanding is that in these early works of this Vilkovinsky, he make a crucial difference when the theory has a gauge symmetry or not, and when there is when the theory is a gauge theory. The metric that you use in field space is not just what happens in the kinetic mixing, but is a projection of this of this GIJ basically, or HIJ as you call it, on the space of the gauge orbit. And these introduce non-local operators and a bunch of complication that I don't immediately see in your presentation.
Yeah, I think the difference is that I don't think he was using a full background field gauge fixing approach. It's kind of a critical thing that was different.
So it has to do with the, because again, what
I don't think he's doing the background field method there, which is leading to the complications you're talking about.
Okay, because what is at least is stating in all this work is that you can either compute things such as the one loop effective action and so on with the, let's say, with the GIJ that immediately appears in the metric, so sorry, in the Lagrangian, or this non-local metric, but you have to use, either use the non-local metric and then you can do in the gauges you want and you obtain a result that is covariant and gauge independent, or you use the metric that appears in the action and a specific prescription for the gauge, and then to obtain the same result. That was the, so I was wondering.
Yeah, but I think in both cases, he's not actually using the background field method in the way that we're using it here. So what I was trying to emphasize, I got a bit compressed for time. The background field method is kind of critically important here in terms of the interfacing with the geometric approach. So if I can go back a little bit, we actually found this doing the background field method first. So what I mean by this is this gauge fixing term here, and putting this geometric structure in the gauge fixing term. This is something which you should think very carefully about, right? Because what this is essentially combining up the perturbative and non-perturbative expansions of the theory. This is the important thing to really understand, which is related to your question. If you try and gauge fix in a way that's not modifying the non-perturbative expansion of the theory, you can do that, and various correction factors will appear in the theory. And that's exactly what you're talking about. Okay, and that's what was appearing in his work. Alternatively, what you can do is you can gauge fix in a way that preserves the background field gauge invariance in a way that combines the non-perturbative expansion of the theory into the usual gauge fixing structure of the theory, which is usually just associated with the perturbative expansion. All right, and when you do that with this gauge fixing term, those effects being combined up cleans up a lot of the correction factors that are essentially being introduced associated with what you're asking about. And that leads to much. Sorry.
Yeah, this gauge fixing parameter that you have here, this psi at the end appears in the. No, I guess it disappears.
It disappears, but the point is, it's a nice way of gauge fixing. Then you can look because then you're basically. So essentially, what I can say in terms of words is, if you gauge fix in a way that doesn't preserve the background field structure of the theory that you're trying to build in, then you need to do a whole bunch of correction factors to basically reestablish that background field structure that you want to build into the theory. Now, that's what he was doing, and that's what the corrections that you're talking about, which is a big, complicated mess. You can do it, but it's a mess. The easier thing to do is to gauge fix in a way that preserves the background field configurations. That's the gauge fixing term I just showed you. And then when you have that, then you have on your hands kind of a beautiful simplification. And essentially, the background field, the shift of the background field that the theory is independent of that because you've gauge fixed in a way with perturbatively and non-perturbatively, importantly, that doesn't affect the background field configurations. So you know that this variation is zero. And then from that variation being zero, you get consistency conditions in the field theory relating the different endpoint functions. Okay, and that's a much simpler structure to the theory in terms of its gauge fixing.
Okay.
So, but it's important that you essentially have to start to realize that you have to gauge fix on the curved manifolds and preserve them, not mess with them as background field configurations. And as a consequence, logically, it combines the perturbative and non-perturbative expansion of the theory into something that has to be cross-consistent with each other. Okay, that's why I was emphasizing later that, you know, this cross-consistency appears in the gauge fixing of the theory and has consequences in terms of the calculational results for loop effects and dimension 8 effects.
Okay, so, okay, thanks a lot. So in principle, you would say that you would obtain the same result with these formulas, but in a much more complicated way, because as far as I remember, you're already doing this, that formula is with this correction where U1 fields, it was a mess. So I cannot imagine for the standard mode. Yeah.
You can do it the hard way if you want.
No, okay, I was just wondering. So the two things,
yeah,
okay, so the crucial thing is to choose this way of gauge fixing that
that's right.
Okay,
and you can understand conceptually why it should help you, right? Because you're gauge fixing in a way that doesn't break. It's just like BRST invariance, you know, in the usual approach of the background field method for gauge fixing, right? You have a symmetry of the theory that you want to preserve. And then you can gauge fix in a way that preserves that symmetry, or you can gauge fix in a way that breaks that symmetry. And then you have to correct it with BRST and all that sort of things. You can do it and it'll work. It's just really hard. In this case, we have a symmetry that's also embedded on, the symmetry is also related to the possible deviations leading to curved field spaces. That's what was showing up in these constraints in terms of the zeros and the off diagonals for the square roots of the metrics. So you can gauge fix in a way that doesn't respect that. And then you have to build in all sorts of correction factors, or you can gauge fix in a way that respects that. And then it's much simpler. And it's really non-trivial how, when you do that, the Lagrangian parameters that appear in combinations are things like this Z mass here. Okay, so this is really quite a tell in the field theory that when you do it this way, the usual concept of a Z mass is being generalized consistently without any kind of crazy correction factors into a Z mass associated with the curved field space. This was the thing that really, for me, was like, okay, this theory is geometric. This is the key sort of thing to make you understand that that's what's happening in the field theory.
Okay, thanks again.
Oh, and also I should just mention, I am available for the next couple of days. I'm going to be in Madrid until like the 15th. So if people want to talk directly, I'm very happy to go over things in more detail. And, you know, we could look at some math together if you wish. I am just around. So I'm kind of here just chilling out. So if you want to talk directly consistent with COVID restrictions in some cafe, then let me know. It's fine.
Perfect. So Maria Jose, do you want to ask your question?
May I, or it's too late?
If it's very quick.
I'm fine. So other people can run if they want to, but I'm fine.
Okay. Let me make a very short comment. If you compare this case, the SMEFT, with the nonlinear case, the HEFT, as you know, in the case of the nonlinear case, it is implicit, the main conclusion that you are saying. In other words, regarding phenomenology, the fact that dimension 8 in the SMEFT, dimension 8 and loop go together, the effects of the dimension from the dimension 8 operators and the loops from the lowest order operators go together, is implicitly included in the nonlinear approach. Remember the chiral dimension counting in the nonlinear approach that is telling you that the loops that you compute with the lowest order chiral dimension, lowest order Lagrangian, go together with the next order in the expansion of the chiral dimension. In other words, in that length, the loops that you do with the chiral dimension 2, which is the lowest order, go together with the contributions, three-level contributions from the highest dimension operator, which in this case are 4 chiral dimension.
Yeah, I see why you're saying what you're saying there. Yeah, I think I see what you're saying. Yeah.
Let me conclude my thoughts about this.
Sure.
It sounds to me that this interesting job that you are doing with this dressing of the fields, it sounds to me that the nonlinear part is included in the geometry, in the connection that you are putting for the fields. And what you are living outside is really what incorporates the gauge invariance and all the effective operators. So don't you think that at the end, the connection that you are talking about would be the nonlinear approach, finally?
So what I would say to that is the way we're defining the connections with the resummation of all the scalar emissions and essentially a resummation of the v squared over lambda squared expansion, that you can think of that the way I presented it here. And you can do it in the SMEFT, and it gives you calculational power in the SMEFT, where when you then expand out those structures, which are general structures at some points in the analysis, when you expand them out to fixed dimension, dimension 6, dimension 8, dimension 6 squared, that sort of thing, then you get back to a way of calculating the subleading terms in the SMEFT. If you were to not expand those things out and not have the symmetry-based relationships between things that happens when you gauge fix the theory in an operator representation and you go to a fixed order in the power counting expansion, then I would agree that the relationships between observables would be relaxed in a way consistent with things that are happening in the heft.
Okay, there are many things to comment, but I will do in person with you these days.
Yeah, we can talk directly. I'm fine. If you have some time, just let me know. It's no problem.
Let's see if the COVID allows us to do.
Well, whatever the rules are, we should be consistent with. But and I'm assuming we can meet in a cafe or something if you want to.
Sure. Thank you very much. Anyway.
Yeah.
Okay, I think we can thank Michael again for this very nice talk. Thank you, Michael.
Sure.